Okay, what I want to talk about today, and I kind of mentioned yesterday in at least one of the lab sections, if not both, that I've pretty much covered what's going to be on the final from an academic standpoint. There's a few odds and ends topics I'm going to pick up, but probably 90% of what's on the final has already been covered. However, one of the topics that is on the final exam that there deals with the stack and how it's used with interrupts and how it's used with subroutines. Yesterday we did a lab on using subroutines, and I wanted you to look at the stack. I don't think most of you caught what I was talking about when I was referring to the stack. So what I want to talk about a little bit today is how the stack works, what it's used for, and the purpose of the stack. Now, the stack, when I talk about the stack, let me first off define what it is. It's a region of RAM, right there, used for temporary storage. Now, its primary use is to store the program counter, and for some reason this is, that's kind of interesting. My pen is, when I get close, it's putting a small one out there. So my handwriting is going to be worse than average today. My handwriting is never good writing on this thing, but it's better. I prefer to write on this so I can record the lectures versus using the whiteboard But this is register, is what that is. Register. Or region, region. Right there, region. So what it is here's RAM right here. Temporary storage. Right there. I'm sorry, with this pen doing its thing, my handwriting's gotten worse up there. And sometimes I speak. So if you can't read it or don't understand it, do what you did up there. Okay, it's for temporary storage right there. Its primary use is during function calls and interrupts. It can be used at other times, but it's what it's normally used for right there. So it's normally used, and in particular, the program counter is almost always stored directly onto it right there. So whenever yesterday you had a line, a code that said call, add to num, right? You had that line there. Now, when you did that, what that does is in the and I didn't bring my board with me. Matter of fact, I need to stop and see out detail where I stole the boards from her office. There. But when I call that there, this is a place in memory, in code memory down here, add to num. Right there. Right there. You know, there's two dots here. That's a label. This is a label right there. Right there. Now, in C, you would write a function. In assembly language, we don't have a format. We don't declare a function or variables we pass to it because there is no way of doing that. We just simply place the label there. It's assumed that my main code ended here. This is the end, and this is not there. That is the end of main right here. And we don't have any syntax where main. This is, I don't know, there's some setting that screwed up on my computer here. I don't know what's going on. Okay, but this is the end of my main routine. If you're working in C, right there, page. Right there. If you're working in C, you would have a function here called void. It'd be a type void, main, and you pass it void. And that's annoying. Right here. There's the beginning. Now it's not writing at all. Right there. This is your main code right there. This is main. That's your main C program right there. And then down here, I would have another variable that would say, right here, and we'll just simply say this is an int, and add, and this is also to num, right there, and we pass it int n1, and this is n2 right there, and then we have some code right there. That's the way you do it in C. Now what C does is it takes this and converts that into an assembly language subroutine, and it puts at the end of that a return right there, and it uses the stack to push and pop these variables. We're not going to worry so much about that right now. Well, I will talk about that in a minute. But C, that's how we write subroutines. In assembly language, the way we write subroutines is that we basically, here's our org 0, then here's our long jump main, and, well, I'm sorry, that is almost impossible to read, but that there. And then we have some other things, and here we have main. Let me plug this. This might help me some. Right here. And let me just put it down later. This might help me some here. But we have main here, right here. And that's a label right there. And then we have our code. And normally here, I put a jump to start right there. Is what I put in yesterday right there. I did a jump start, and start was somewhere in here. That's a label right there. And this was all my initialization stuff, initialize stuff. That's where we set up our ports, we set up our timers, or whatever we did that. That's where we did that there, and then here's the start of our code, and then here we had our call add to num right there. Now this call add to num, as it turned out in our case yesterday, was at the very end of main. It doesn't have to be at the end of main. It could be anywhere in the code that's there. So when we saw this later in the code, we can add a bunch of other stuff there. We have add to num right here. This is the label right here, and then here's our code for add to num, and here's how we end our function right there. So this is a function that we're calling. That's it. Do you have a? I still don't understand.
So you can see the main area.
Oh. Okay. Okay. I'm sorry. The projector doesn't. Oh, I see. The bottom of the lens is covered by the bracket. Okay. So, all right. I'm sorry about that. Okay. All right. So this is how we define a function in assembly language, right there. So that's the equivalent of here void. We have a function here, add, right here. I'm just going to call it add. We have our variables that we pass. This is the beginning and the end of our function. These two are very similar to each other, right there. Now, the big difference is that we can't pass variables very easily with assembly language. We can, but the way we would normally pass variables is that we would have to push them onto the stack right there and pop them off. I'm not going to get into that in much detail simply because it gets a little messy, because the way that the assembly language uses the call is that it also pushes the return address onto the stack right there. So what we have to keep in mind is that we have to, if we use the stack and we pop off the return address, then we have to push it back onto the stack right there. So, okay, with that said right there is that what happens here is the stack. Is what I want to talk about. It's a place in memory right here. Memory starts at 0, And what is my pin doing here now? 0, 0, right there. Remember, our data memory only has 256 bytes to it, right? That's all we have in our data memory. The stack pointers points to location 7 by default. Got that. Now, when we write to the stack, we don't write to location 7, we write to the next location. So if the stack pointer says 7, we're actually going to write to location 8. So location 7 happens to be R7, R0 is location 00. So the stack pointer points to the place in memory just above R0. Now, that's a little bit dangerous because if we use bank 1, remember we have 4 banks of our registers. Banks 0, 1, 2, and 3. Bank, and now what did that one do? Right there. Bank 0 is 0 through 7. Bank 1 is locations 8 through 15. Bank 2 is location 16 to 23. And bank 3 is location 24 to 31. Those are our four banks. And I'm not going to cover it today, but there's a special function register where we set a bet to change what bank we're using right there. The default bank is right there, 0. Bank 0 is our default bank right there. So if we want to use bank 1, we change our register bank to bank 1 by changing the special function register. There's just a bit we set to change it to 1. We change to bank 2 by changing another bit. Change 2 bits to change it to bank 3. So there's a special function register to change our banks. Well, the stack pointer overlaps bank 1 right there. The other thing we've got to be careful of is every time we do a call, we push the return address onto the stack right there. Now, in programming, we have something called recursive functions. Did you guys cover recursive functions when you took C? Does that term mean anything out there? A recursive function is one in which it calls itself. Right there. So let me talk a little bit about recursive functions and why they're a problem with microcontrollers. Right there. A recursive function, it's called recursive. Right there. That's almost readable. I don't know if it's spelled right or not. Right there. Recursive function is a function that calls itself. Right there. Okay. You probably have seen it, you probably don't remember, don't use it. There's something called Fibonacci numbers. Right there. Right there. And factorial. We'll just call it factorial. 5 factorial is equal to 5 times 4 times 3 times 2 times 1, right? Well, I can write 5 factorial as 5 times 4 factorial, right there. That's just another way of writing it. So I can write a very simple C program that says int fact, right there. I pass an int n, right there, right there. And I say if n equals 1, return return 1, else return n times fact n minus 1. Right there. That's my function to find n factorial. Right there. So what I'm doing here is this is the function fact, and I'm calling itself within that there. So every time I call this function, it's going to be pushing the return address back onto the stack. Right there. Now we could do this in assembly language. It's just kind of easier to show it in C. What I'm trying to get across is this idea of recursive programs. And recursive programs will quite often, or subroutines will quite often result in many, many calls back, function calls, right there. So, and what this particular function does is if I pass it pi factorial, it's going to return back 5 times 4 factorial. Well, 4 factorial is going to return 4 times 3 factorial. And then that's going to return back 3 times 2 factorial, which is going to return back 2 times 1 factorial, which returns back 1. Right there. So I end up with 1 call, 2 call, 3 call, 4 call, 5 calls right there. So as a result, every time I call the stack, I require 2 bytes. Every function call, right there. Every time I call a function, I use up 2 bytes on the stack, right there. And the reason I use 2 bytes on the stack is the program counter is 16 bits wide. Because the program counter count points to a location in code memory, and code memory can be up to 64K in size, right there. So it's got to be that there. So in this particular case, I'm going to use 10 bytes on the stack. Now, 10 bytes of memory doesn't sound like a lot, does it? That there. It doesn't. But remember where my stack is located. It's located at location, starts at location 8 and goes up. So if I'm using bank 2, for example, then I'm going to overwrite that. If I'm using memory location that there. So you have to be aware of where your stack is and how much you're going to use it, and make sure you don't overwrite the stack. Because if I overwrite the stack, then I lose my return addresses and my programs go off to lunch. That there. They go out for maka and never return back. Right there. So they don't know the way home. Right there. So that's why you've got to be careful with the stack. Is that the stack will is the return back. Get there. So when we look at our stack is what we used it for yesterday. That there. And when we were running this yesterday, right there, we used that yesterday. We had the call right here, add to num. Now what I wanted people to do is I put a breakpoint here. And what I wanted you to see is when we stopped there, we had the program counter here, and most of it was 081D, I think, was something like that, right there. That's what the program counter said at that point there. When the stack pointer was down here, and it said 07 right there. When I did the one step, and the program counter, the pointer would have pointed right here to add to num, right there. And then your first line of code, which was move whatever, right there. The program counter, this would have gone to say 082F or something like that. I don't know what number it was, right there. But 082F, I was just making a number up that there. This would have gone to 9, right there. Because now my stack was pointing to 7, which is actually 8. I wrote in these 2 locations my return address, and now my stack was pointing to here, right there. So if I would have gone into my RAM, and I would have looked at memory locations 8 and 9, I would have seen 081E probably. 1E right there. Oh, well, that doesn't help either. Our projector is not on the screen centered up there. So what we see that there is that our memory location right here, location 9 is where our stack is located. That contains the address right after this one right here, which happened to have been the jump command, I think, in most of our programs. I think a couple of people I sat down and put a bunch of no-ops in there to show that it points to the next command, next line that there. So that's what the stack does right there. When I hit the return, our return line right there, at that point, the stack pointer goes back to 7 right there. And the programmer counter goes down back to 081E, I said right there. Right there. So it tells us where to go back to, is what it's doing right there. Because in terms of our program flow, what we want to have happen is we're going through here, we hit our call command, we go off here, here's our function right here, right there. We run our function, we hit our return command, and we go back to where we were at in our code. This is the program counter where we were at. We add in a couple of bytes because the call is going to have 2 bytes for actually, if it's just a call, it'll be 1 byte because it's a local call. If it's an L call, then it'll be more than that. If it's an absolute call, there's more than one type of call. And depending what type of call you give, tells it how far it's going to jump right there. So, but what we're going to see, I'm just going to worry about the call command. We go off that there. Here's our function right there. Now we don't have the word function. We don't have a function header like we do in C. We don't have a prototype we put in there. All it is just a label in our code. That there. The call, the return is going to just simply tell this to pop the return address. And that there. Now, some terminology is when we put something on the stack, it's called push. We push data on the stack. Push is the same thing as store on stack. Right there. We store the information on the stack. To retrieve the information off the stack, we pop, retrieve from stack. Right there. So that's retrieve. So we got 2 terms. We say we push something onto the stack, means we're storing it onto the stack. When we pop it, we take it off the stack. Another term that you need to be aware is what's called last in, first out, right there. Last in, first out. In, first out. Now, what this basically means is that when we push something on the stack, the last thing we push onto the stack is the first thing we pop off, right there. So if I want to store some information onto the stack, and then I want to pop it back off, which quite often we will do inside of a subroutine, or inside that there, we will often do is that here's my subroutine, XYZ, right there, and I'm going to push R0, push R1, push R2, push R3, and R3. Now, we do all 7, doesn't matter. We have some code, we run some code, and I want to pop the reason we want it there is we want to save these. We want to save them so when we finish our subroutine, we can put it back the way it was, right there. So at the end of this, we're going to pop it back off. Pop R3, pop R2, pop R1, pop R0. Now, what you should notice here is that these are in reverse order right there. Right here. That we pop it, we push it R0, R1, R2, R3, we pop it out R3, R2, R1, R0. We reverse the order. The last thing we pushed onto the stack was R3, so the first thing we pop off is R3. So that's where that last in, first out comes into, and you'll see that term used when we talk about stacking. Someone throw water from the roof, from the balcony above. Like, hopefully no one's standing underneath there. I don't know, did anybody else see it? It looked like a bucket of water was thrown off the balcony out there. So, but this is what the stack, this is how the stack is used right there. Right there. Now, depending on the processor, and I'm just drawing a blank, I didn't look it up ahead of time. The interrupt works the same way. The only difference is the interrupt will save some additional information right there. Now, quite often, if you want to pass variables in a high-level language like C, then whenever I do let's say I have a function written in C, add to num, right here, and I pass N1, N2, right there. You know, this is a function right there that I call, you know, let's say sum is equal to, right there. That's a function call in C. Quite often, what this will do is it will push N1 and N2 onto the stack, and then return it back. Now, C is very complicated in how it does passing variables, because C, I don't know, are you aware of the difference between passing by reference and passing by value? Does that ring a bell when you deal with C? When you work with C, you have two ways of passing variables, right there. So if I have a function here, let's call this int add to num, I'm just going to shorten it right there, and I say int, if I say star n1 means that I'm receiving the address for n1. If I just say n2, I'm receiving the value. If I receive the address means that I can change n1 in the function, and when I return it back, the value of n1 has changed. If I receive the value and not the address, means that I can use n2 within my function, but I can't change it. I can change it within this function, but when it goes back, it'll be restored back to its original value. So they call that, this is called pass by reference. By reference, which means we pass the address. This is pass by value. Right there. So you can pass it different ways. And the reason I bring this up is in more advanced assembly language programming, quite often we will write assembly language subroutines that we're going to call from C. More water coming out there. So you have to know if you're going to be calling a function you're writing an assembly language, whether you're going to receive an address or whether you're going to receive the value right there. So there's some differences. I'm not going to get into that in this class. This is an introductory level class to microprocessors. It's not an advanced course in assembly language programming. So I'm not going to worry about interfacing C and assembly, because you can do that very easily. I can write 90% of my code in assembly language and write certain functions in C that are time sensitive, that are very hardware specific. And matter of fact, most large projects that have any code that has to be run in an assembly language will do it that way. They will mix the two languages right there. Like I said, I'm not going to get into that. There's a lot of little tricky things that, that there, because when you look at this there, because when you do the pushing and the popping, then you have to skip over the return address, pop the information off, put it in temporary locations, and then you have to push back the address and then push, or push the data back in and then push the address up there. So if you're going to be doing that, you're going to have to pop off, that there, and I'm going to call it pop off, and I'm just going to say some location that they're X, Y, Z. Well, that's location memory. That's the program counter right there. You pop off the program counter, that's 2 bytes, X, Y, Z 0 and X, Y, Z 2. Right there. That's 2 bytes that you have to pop off right there. Right there. Because the program counter is 2 bytes. Then you pop var2, pop, well, we'll say num2, pop num2 0, num2 1, and got there, and then pop off, see, and then getting to the arrow is the high order byte, low order byte first. If you're dealing with C, it gets quite messy very quickly right there. So I don't want to get into that detail right there, because when you mix languages, you have to understand how the compiler is going to push things onto the stack, and then look at how the compiler is going to pop things back off, and you have to match that in the assembly language code. Back in the early days of 8086 assembly language programs, we used to do a lot of things where we would push things onto the stack and call DOS interrupts that there. And we had to sit there and study the DOS manual very carefully to see how all these interrupts work out there. Fortunately, we don't do it that way anymore. So, out there. Okay, the only thing different now is when we deal with interrupts. Right there. And what an interrupt is that it's a function called by the micro P or micro C, either one, microprocessor or microcontroller, under certain conditions. And I don't know why it draws that thing as it makes my O's into really nice, neat circles. I don't conditions. Right there. So, we had, for example, and I talked about interrupts a couple classes ago. I posted notes, I think, to the lecture notes up there. The 8051, the F120, which is where those slides came from, has 22 interrupt sources. Right there, that's the F120. We have about 18. We don't have quite as many as the F120 because we're using the 850 processor. It's only got 2 external interrupts, interrupt 0 and interrupt 1, and it's only got 3 timers instead of the 5 timers that you'll find in the more advanced processors. So, but these interrupts right there, these are hardware interrupts right there. Some are hardware, some are software. What I say, they're almost all related to some type of hardware, even though when we say they're hardware, but they're the timer interrupts that those are set up basically. We have a register bank, a set of registers, T0 for example. We have a high order byte, a low order byte, and now it's putting squares in for me right there. Right there. So, unfortunately, one's a rectangle and the other's a square. Regardless, we load this with a number, say FFFF, right there, FFFF. We add 1 to it, check if it's 0. We add 1 that there. When this overflows, it generates an interrupt. Right there. We'll talk about timers in a little bit more detail when I get back. Next week we'll talk about timers in a little bit more detail. But what a timer basically does is we set it up with a value in every clock cycle or every 2 clock cycles, however we set it up, it's going to increment the timer. When it overflows, it generates an interrupt. Our timers can also be used in other modes. So that's normal. And then when it generates an interrupt, we go off, we execute some code, and that's a function, a subroutine that's called, or it's now called an interrupt service routine. Right there. We talked about that. An interrupt service routine is very similar to a function. The big difference is, right there, and you can do this multiple ways. In assembly language, we would normally have timer 3 interrupt, for example, right there. Now, what we can do that there is we have our code and we have a return from interrupt right there. It functions the same way as the return does in the previous one. It generates the return address right there. I'm not going to quote off the top of my head which registers are saved, which ones are not. Usually, a number of the registers, the flags are almost always pushed on the stack, and some of the registers may or may not be. For some reason, I'm drawing a blank on the 8051. It's different with every processor. And it actually varies a little bit with the compiler you use, too. We're using the Kyle compiler, and that may be different than, say, the GCC compiler, for example. You know, assembler right there. Different assemblers may generate different codes on that there. That's usually on C. On the assembly language, it's pretty much fixed by the processor. I'll take that back. But what happens there, and then somewhere at the top of your code, before we had something that says org 0 and then long jump main, right? Right there. That's what happens right there. We would have another org, and I'm just going to say XXX, and we would have a long jump timer 3 INT right there. And what this does right here is we point this to the location in the interrupt table right there. That works with every compiler. Now, other compilers have different ways of doing that there. But ultimately what that does, and I don't know, let me see if I've got it here. Right there. I'm looking for the 8051 data sheet right there. Well, actually, if I go to processors, actually, if I pull up lab 4 on here, I know it's like an 8 on this here. This is where we had it before. This is the lecture I gave a couple of weeks ago. Right here, you will see right here. Again, all right, I will take that back. This slide does show it does push the registers on the stack. For some reason, I was drawing a blank whether or not the 8051 does. So the registers out there, and I pointed out, and I'm just kind of reminding, I went through these slides already, that you should know this slide right there. So I'm just repeating obvious, but that there. This is the interrupt vector table right there that I was looking for. You'll notice here the interrupt 0 reset is interrupt vector 000. Going back to what I said here, I had org 000 right there. That is the interrupt vector for the reset. The reset is an interrupt right there. So if I want to use the timer 3 interrupt right there, the timer 3 overflow is 73 right there. So going back to this right here, I would put 073 hex right there. Hex right there. Is that XXX? That's the address I would put there. So this is what happens when an interrupt occurs. That there. And I'm not going to go too much onto this because next week's lab, what I plan on doing is we're going to use interrupt 0. That there. And now interrupt 0 is set up in such a way, let me bring up, and I'm going to cheat. What's the Dow Jones? Don't cost me any money here. Right there. This is done. Okay. Up there. But I bring up the configuration wizard right there, and I don't know if I showed this. I showed this program before. This is a tool that Silicon Labs kind of gives us to look at setting up our processor right there, and it gives us all the tool code that there. And what this does is it saves me from looking things up in the data book. Right there. I found it to be about 99% accurate. Once in a while, it makes mistakes right there, but 99%. So all this software package does is I tell it how I want to configure the chip, and it generates the code to do that I would normally get if I went and looked through the data book and said, how do I set up enable interrupt INT0 to be an active high and to put it on a particular pin. This gives me the code to do that right there. So right there. You have to know exactly which processor we're using. We are using this top one, the smallest one. I finally found that to be the right one. Digging through a number of data sheets. So we're using the 8051F850-ZU, George Uniform, / Indiana University. Right there. GGU-/IU. Right there. We select that there. Right there, you can see that tells us which processor we're using. And what this is generating right here is code format. We can tell it assembly language. This actually generates some code that we can actually just include with our main program and just put it in an include line like this right here. Right here. We give this a name and we just include it with our code right there. Or we can cut and paste it and put it in our code right there. So that's there. So if we want to use our peripherals and we want to use interrupts right here, the first thing we need to do, if we're going to use any interrupts other than reset, we have to enable all interrupts. Now, when we enable all interrupts, that doesn't mean every interrupt is enabled. It just means that we globally have enabled interrupts. We have to enable each interrupt we want to use individually. But if we don't check this box, we won't have any interrupts enabled right there. Right there. So we can do a ADC0, end up enable conversion complete, enable the window comparator for ADC0 right there. We can enable external interrupt 0, which I'm going to enable there. We can enable any of our 3 timers right there, interrupts right there. We can enable a port match right there. We can enable our PCA, which is our programmable counter array. And these are our 2 serial ports that we can enable right there. So once we set those up right there, somebody is sending a message. Make it wait. Somebody in my digital class is asking a question. All right. So once we do that there, and then we've got our interrupt zeros. Now here is where we set them up to be active low or active high. Right there. We select our pin we want it to be. Unfortunately, I was going to add the interrupt yesterday to the class, but we cannot use ports 1.7 or the only place we can use interrupt 0 is port 1 or actually interrupt 1. They all have to be on port 0. Port 0 is the only port that we can use for our interrupts right there. Right there. And I believe one of the ports is also tied to the analog there, so we don't want to use that port. So I'm going to say 0.0 right there. And we also want to tell that if we're going to use that for an interrupt, that we want to skip that pin for digital I/O purposes right there. So we have multiple things we have to do. Just kind of repeat that there is if we're going to use, and I have to unplug this, I'm sorry, here, right here. We also have to enable the crossbar here. And I don't know if I can plug this in, you can see that there. See, we have to also enable the crossbar right there. So, but we want to skip that pin because these are our various options of that pin that are assigned. And if we don't tell it to skip that pin, then the crossbar will assign it to something else. So if we want to use it for an interrupt, we have to skip it in the crossbar right there. So, and remember the crossbar's job is to assign all of our various peripherals to what I/O pins we have out there. So when we do this, again, I have to unplug that there to right there. And I'll probably have to plug it again, right there. See that there, matter of fact, let me just go ahead and hit the OK here. Right here. This generates some code for us, right there. And right here, move into port 0 skip. That's a register in the special function registers. And we're telling it we want to skip location 001, right there. You know, if there's a 1 in that, if there's a 1 in that particular, you know, there's 8 bits. If there's a 1 in a particular location, that pin is skipped. So we're telling the crossbar that we're going to skip pin 0.0. If we told it we wanted to skip pin 0.1, it would have right in the move into PO skip, P0 skip 0.2 right there. If we wanted to skip the third pin, it would write 4. If we wanted to skip both 0, 1 into P0 and P1, in other words, we want to use 2 external interrupts, we would write in there 3. We would put a 1 in both of those. But since we don't want to look that up there, I don't remember where P0 skip is. I don't remember the name of that. But if you looked it up, that is a special function register that tells the crossbar to skip those pins when assigning pins. Move XBR2040, that enables the crossbar. That's the code for enabling the crossbar. Right here. Right there. And interrupt initialize, we're going to move into the interrupt enable register 081. That enables 08 enables all the interrupts, and 01 or the 1 tells it which interrupts that there. But that particular special function register, i.e., is telling it what interrupts we want to use right there. And then there's multiple registers that there, and move into interrupt T0FC, and I can't remember what interrupt flag that stands for, 000, and that's telling it, that's also setting up our interrupts. So this is how we set up our interrupts right there. So we can actually just copy and paste this code, put it into our code, or we can save this and do then I'll be writing a lab next week where you'll be doing this with P0 and P0.0 and P0.1 on the 2 interrupts. And what we'll have to do, because there's no push buttons, we're going to have to put a little connector on the back and just touch it to ground to simulate the interrupts up there. That's a very easy thing to do. We just put the little jumpers on there. You haven't used the jumpers yet. The other class used the jumpers with the keypad up there, for interfacing. But we'll just put a little jumper on the pin and just touch it to ground to show that that's the same thing as generating the interrupt. And we'll put breakpoints in, and you'll see it when we touch that to ground that it'll go to our interrupt right there. And then we can single step our way out of the interrupt right there. So we will go through and we will do that, and we will set up the interrupts right there. And then we'll also set up the timer interrupt. I'll probably go into a little bit more detail on the timers right there. The slides for the timers is right here. I'm not going to go through them today simply because, one, it's a very long set of slides. So next week we'll go through them there. But the timers, we've got multiple timers that we go through, and the timers actually go through and set up interrupts as well. And I need to cover the timers. I said I pretty much covered everything, but the timers are mentioned a little bit on the exam along with the serial ports. Not in great detail, but I want to just kind of hit both out there. So we're going to talk about the timers yet. We'll do that next week after the lab. Next week's lab is just on interrupts. And we'll deal with, it'll be a relatively short lab, not much longer than yesterday's lab. Matter of fact, it'll be even shorter because we won't have to add 2 numbers. All we want to do is see that gets into the interrupt right there. So what we'll probably do is we'll probably go into a routine, turn on an LED, flash a couple LEDs or whatever, and then jump back out right there. So, but what we're going to be doing is writing an interrupt service routine, and we're going to be setting up the interrupt the external interrupt for an active low, so we can touch it to ground, and we may do an active high on. Doing the active high is a little tricky because if you enable the weak pull-ups, it's going to pull it high unless you hold it to the ground. So we'll probably have to do active low on both of them back there. So, but we're going to use the 2 external interrupt pins right there. And I'll probably write the lab. Knowing me, I'll probably write the lab next Monday afternoon, about half an hour before class. Yeah, that's it. But that's what the lab's going to be, is on how to use the interrupts right there. How to set the interrupts and use the interrupts. So right there are multiple interrupts. I'm only just using the easiest ones. That there. Going back to my interrupts right there. As you see, we have a lot of different interrupts that we can. Right here. There's one page. There's one page of interrupts, 2 pages of interrupts. Right there, 2 full pages of interrupts, and that looks like somehow that slide got messed up that there. I don't know what's going on that there. So that there, I won't save that slide because I screwed it up. Right there. So there's one set of interrupts right there. There's the other set of interrupts right there. There's 2 pages that there. Again, you can see that we've got the ones that we've been using. For blinking, we use the timer 3. No, we can use the timer 3 interrupt. I talked a little bit about that. The timer 2 interrupts are very commonly used. We also quite often will use in the bit diversion right there. Now, right there, no, I'm getting confused here because my microcontroller course, we actually have used the analog to digital converters, so we've used those interrupts in that class right there. We won't get into the A to D in this class right there. So if there is an A to D on the board, and there's an little potentiometer where we can do the analog, but that's more for the interfacing course right there. So, all right, with that said, I'm going to kind of wrap that up. I'm not good for a good 2 hours, but as I said, we're in really good shape on the syllabus. I'm not too worried about ending classes early. I'm not a fan, and I don't play by the rules as much when it comes to running 2-hour lectures, because that's there. So that's there. Any questions on interrupts? Well, let me rephrase that. Interrupts, hold your questions until we do the lab. That's there. Is there any questions on subroutines in the stack? How it works? Right there. Keep in mind that I could very well ask a question where I say, I have to go there, and I may ask you, what does the stack contain at a certain point? Right there. So that there. So think about that when you think about the stack, and if you want me to do some examples during the lab on how that stack works, we can look at it. The easiest way to see how the stack works is to watch it during the lab. That there. Me going through and writing down what happens in the stack by hand is not quite as easy, and that there. If we have confusion next week after the lab, I will bring in the board and I'll kind of go through some demos on how you look at the stack and how it's being manipulated. Because we can have the situation where we have a function, and let's just throw this out here. We can have the situation where we have a call here, and I'm just going to call XYZ right here. Here's XYZ. Right here we have the code. And then I can have in here a call ABC right there. And ABC is somewhere else here. Here's ABC right here. Here's our return for this one. Here's our return for this one. Right here. And what does the stack contain at this point here? At that point, it's going to contain 2 addresses. It's going to contain the address to get back to here, and then it's going to move the pointer, because at this point here, I've got, up here, it contains 7. The stack pointer contains 7. After the call, here it's going to contain 9, the stack pointer will, and it will contain the address on the stack to get back to here. After here, when I get to here, it's going to contain 11, or B, right there. And it's going to contain the address to get back to here, plus the address to get back to here. So it's going to have 2 addresses in it. So I'm calling it that there, and that's where you've got to be careful on how, I mentioned the recursive routine, how many functions are called, because you've got to have enough room for multiple there. So if you get, if you get into the case of n factorial and you pass it 125, that means you need 125 bytes or 250 bytes on your stack. Well, the 88 or the 8051s only got 256 bytes of memory. You're overwriting the special function registers at that point, right there. You completely wiped out all your special function registers. You completely, that there, as you're doing things, moving things around, you're overflowing the stack, and you're going to have all kinds of problems. So you've got to be careful when you're using subroutines, not to that there. The other place you've got to be careful is the interrupts. You have to disable the interrupt as soon as you get into it so that it doesn't keep calling itself. So if an interrupt keeps calling the same interrupt over and over and over again, you're going to overflow the stack. So the first command inside of a special function or interrupt service routine is going to be disable the interrupts. That there. And then when you finish the interrupt service routine, then you re-enable the interrupt. That there. But while you're servicing the interrupt, you want to disable it and reset the flag. Right there. Because otherwise the interrupt is going to keep calling itself over and over again. Right there. And that creates a huge problem right there. So when we deal with interrupts, we have to clear that. We'll get more into the interrupts, or as I said, when we do the lab. And so when you'll see the first thing is going to be disabling the interrupt. That there. And then when we're done servicing routine, we're going to go back to that there. So in the case of we just touch that there, it may call itself multiple times that there. So with that said, have a good rest of the week. I will see everybody a week from Monday. I don't guarantee I will be wide awake. I'm not sure what time my flight comes in Sunday night, if I'm not mistaken. That's Crippet. Loading my trips. Got it. My flight returns. I arrive back at KOIA at 10 p.m. on Sunday night, so that tells me that Monday I'm going to be kind of, by the time I get back to Stoppock where I'm living, it's probably going to be midnight from KOIA, if not 1 in the morning, which means getting in for my 10 o'clock class on Monday morning is going to be dragging. And by the time I hit to the end of the class on Monday evening, I'm going to be, so you guys might be doing the lab while I take a nap. Which is, how often have I lectured and some of you taking naps?